Welcome everyone to this episode on design and analysis of algorithms. And in this episode, we'll learn a fundamental problem in scheduling, graph theory, and geometry called interval scheduling. We'll learn interval scheduling in three parts. In the first part today, we'll learn about the problem definition. In the second part, we'll consider special case, unweighted case, and we'll see a greedy algorithm. In the third part, we'll go over the general case, weighted case, and we'll see a dynamic program for the problem. So let's start. Most of us have read probably the book on Harry Potter by J.K. Rowling. Now, in Prisoners of Azkaban, Hermione faced a problem. She was a sincere and studious student, and there are multiple courses that she wanted to take that semester. Some are history of runes, some are taking care of magical creatures, some divination, some are on Muggle studies, some on arithmancy. Now, some courses are very valuable to her, maybe arithmancy and taking care of magical creatures, and they have value 100. And some courses like Muggle studies is less valued because she was already Muggle born. But still, these classes have a lot of overlaps. For example, in this case, all three of these classes, arithmancy, taking care of magical creatures, and Muggle studies, they're overlapping. So her goal is to take as many classes as possible within the schedule. Now, of course, if there are multiple overlapping classes, we cannot take any of them together. So we need some magic, or we need to solve this interval scheduling problem where there are intervals denoted by these classes, and we want to take as many classes as possible without avoiding as many overlaps as possible and maximizing the amount of profit that we're getting from this selection. Now, for Hermione, we had a solution, and that was time turner. It was a time machine, and she could take a class and then go back to the same time period again and take the another class which was happening at the same time. But for us, for normal muggles, if we don't have time turner, we still have another magic with us. That is the magic of algorithms, and which will help us to solve this interval scheduling problem. So in this part, we'll mainly focus on the cardinality case, and let me define the problem. We are given n jobs, 1 to n, and each job I has a time period Si to Fi. Si is the starting time of I, and Fi is finishing time of I. For example, in this example, there is time period of 16, and each job, like A, this job has starting time 0 and ending time 10, and we say this job is stretched from 0 to 10. Similarly, another job G is 8 and 11, so start time is 8, end time is 11. So these n jobs are given, in this case n equal to 9 in this example. And our goal is to find optimal computable subset. That means maximum size subset of jobs where no two of them overlap in time. We can see some examples. For this example, if we look at job A and job I, they are not overlapping. Job F is from 0 to 10 and I starts only after 12. So this has cardinality 2. It is a non-overlapping subset. But our goal is to find a maximum such subset, and one can try out and find that the maximum cardinality subset that is non-overlapping is size 4. And there are multiple candidates. One could be, we can take B, then C, then G, then I. We can also take B, C, G, H. There can be multiple solutions, but in all these cases, optimal solution is 4. This is a fundamental problem in scheduling. And as we're talking about this line segments, it is also geometric in nature. It's also a classical question in geometry, as well as graph theory. Now, what is the connection of graph and scheduling? If you think of this problem, we can also denote a graph. So for each of these intervals, we can create one node or one object. And then if two nodes share an edge, that means the corresponding objects intervals overlap. Okay, so for example, here A overlaps with B, C, D, E, F, G, all of them. So A will have edges with all of them in this graph. Whereas let's say I have E only overlaps with A and C. So here E has edge with A and C. So one can see that this is called intersection graph. And in this example, we're talking about intervals, but you can define it for any other object. You can take, let's say, rectangles or other objects as well. And one can see that maximum cardinality interval scheduling is equivalent to finding the maximum independent set in intersection graph of intervals. So in this intersection graph of intervals, for example, if we take the first example of cardinality 2, it was A and I, this independent set. Independent set means they don't share an edge. The independent set is a subset of vertices who do not share an edge. And similarly here, if we take the second example, it's B and C and G and H. Again, they don't share any edge between them. It's independent set. So I'll not formally define independent set. I'll talk about it probably later when you talk about NP-hard problems. But in general, for general graphs, independent set is very hard. In fact, there is something called approximation algorithm, which will again come later, which says that given a graph of with n vertices, it's very trivial to find an independent set of one vertex. And that tells you it has an approximation ratio of n. We can have at max n number of vertices and we have at least one. So n by 1 ratio is 1. It is known that it's actually NP hard to even find a better approximation like n to the power 0.99. So if we prove the n to the power 0.99 approximation for general graphs independent set problem, we'll prove P equal to NP. The message is this is very hard in general graphs, but interval scheduling in this example, even in the weighted case, is quite simple. We'll see how to solve it in linear time. But if we go from just interval to the next step, maybe in 2 dimensions, just line segments, axis aligned line segments. In this case, all are horizontal, but let's say we allow horizontal line segments and vertical line segment, that becomes quite hard. That is NP hard. So what can we try? We can try some simple greedy to understand more structure. And there can be 3 proposed greedy, which is quite trivial. There can be more. One is more from scheduling point of view. Think of a classroom. I want to schedule as many classes as possible. Now, if some request comes and the class is empty, I'll just assign that class to the request. This is called select the available request that starts the earliest. And it seems it's not a good strategy if I take this example. This job is a long job, but it starts here. So when it appears, we schedule it. But the optimal solution was size 4. We could have taken all these 4 jobs. Second is more geometric in nature. Maybe there's a resource and we want to use schedule the smallest length classes as many as possible so that we can schedule maximum number of jobs. But even that is not optimal. Think of this example. If I have 3 jobs, size 3, and size 2 or length 2, then we'll assign 2 here. But optimal will be this 2. So optimal is 2, but we are returning only 1. This is also not good. Third rule is more an intersection graph or graph theoretic point of view, that we are trying to find independent set. So we will remove those vertices which have low degree. And that is another way of saying that sort the intervals by number of non-compatible requests and select the one with fewest conflict. In this case, we'll see this will have all of these 4 will have at least 4 conflict. This will have 5 conflicts each, and this one is having only 2 conflicts. So we'll select this one. And once we select this one, we cannot select this 2. So we have to select this 2 or this 2, whatever, but we'll have algo equal to 3. We'll get only solution as 3, whereas optimal is 4. So none of these 3 ideas work, but luckily the 4th idea will work. And that is the natural idea that we should not just give it whenever some request comes, but as we know all the requests, we will try to give it to the request which finishes first. And the next, then we can use the room for the next request. So ensure resources become free as soon as possible while still satisfying one request. This is the greedy rule, accept the request that finishes first. And in the next part, we'll see why this algorithm works.